All right, so today we are going to improve a little bit on the CXXR20 implementation. So a few days ago, I wrote a CXXR20 implementation in nMigen. And in order to be able to use it, we sort of need a top module for it. Because the actual implementation is pretty raw. It operates on a key, data, counter, and nonsense on. So in order to do that, I needed some sort of interface to access the registers and so on. So the idea is to have some sort of top module that looks like a memory, where we have a chip select, write enable, address, write and read data. And so I did some quick coding before, where I have something that sort of works. But I think we should improve a little bit on it today. So this stream is just a random coding stream. I just I have this slot scheduled on Tuesdays at 7 p.m. So I thought, well, why not? So yeah, the stream is active, and let's go. So the reason why I have this interface is because there is this core by SecWorks that has a top module that looks exactly like this. And I thought, why not just make something similar? So I want to take this whole module and sort of generate this code automatically, because having to write boilerplate or like the same sort of code over and over again feels a little bit redundant. So, and because we have Python at our hands, we can do that. We can just generate code. So let's look at the code. I can make it a little bit bigger. Right. So whenever you create some sort of logic in nMigen, you create a class that extends the elaboratable class. In the init function, you can set up signals and other things. In my case, I've chosen to specify the address width and the I/O width. So the width of the bus and the width of the data that is flowing to and forth. And then I also chose to add some arrays or lists with the signals that we want to operate on. So the idea is that we just create these signals, and we add these signals that we want to be able to change to a list internally. So this code is a little bit messy, I guess. I thought about rewriting this a little bit to make it more simpler and just so that anyone can understand it immediately. So right now I have these sort of access flags where it can be readable, writable, and both. But I think we can make it simpler and just have read and write and nothing else. And these are then added as sort of as a dict, where the key is the address and the value is a tuple of the flags and value. And here's a printing function so that we can see easily what addresses that got allocated for our signals. And then here is the elaborate function. This is where the actual logic is created. So what I've done here is that we check for chip select. So no logic is applied if chip select is low, basically just having zeros on the outputs. And if write enable is high, we implement the logic for the writes. So here I filter out the endpoints where the write bit is set. And then in this switch case, I operate on those endpoints, basically. So here I apply the write data input to the module and set that to the endpoint in question. And if write enable is low, it's basically the same thing. The difference is that I am instead setting the read data signal to the endpoint in question. So an example of how this looks to use, how to use it. So I made a very simple XOR crypto cipher just to make it easy to understand the interfaces. So here we have input data, which is block size bits long, and a key which has the same size, and an enable signal, and then an output data with the same size, and data ready. This one will get high, or will be set to high when we're done. And this is the logic, very simple logic. So we just take the input data and XOR it with a key and store it in the output data. And if we want to, we could rewrite this into a multi-clock, high latency, low logic implementation if we wanted to. Could be fun just to get a feel for it. But anyway, this works as sort of a very easy, simple module to use. So I used that in this crypto XOR example. So here I've made a top module where we use this bus wrapper. So I've added pins for all of the signals in question. So chip select, write enable, address, write and read data. These are just arbitrary pins. They're basically just all over the FPGA. I guess you could order them so that they are organized in a sane way. Now they are kind of mumble around, perhaps. And 32 bits, that's actually a lot of pins. So yeah, the routing here might be a little bit complex, but yeah, it works. All right. So again, we create our bus wrapper and our cipher, and then we connect the signals. So in order to make it even simpler, I chose the block size to be 32 bits because in the bus wrapper, I am using 32 bits wide bus. So we don't have to translate the signals. We don't have to expand them into multiple registers. We'll get to that later. And then here I just connect all of the signals together. I'm sure you can write some boilerplate, like some convenience function that does all of this for you, but yeah, I haven't done that. All right. Let me see. Okay. Yep. Okay. So again, sorry for that. Here is the code. So if we want to try this out, we can just run it like this. and it will synthesize a simple design that is actually built for hardware for the ESP5, and we will see that here. So we can see the LUT count and the timing result. And I'm sure you can boost this even higher by increasing the frequency of the clock. So if we say, for example, let's run it at 100 megahertz, we will get a different timing. Oops. It's a little bit random. Anyway, doesn't really matter. What matters is that we now have a top module, so that's kind of nice. So what can we do with this? Yeah, so the idea is that you can hook up all of the pins of the module. So this way we are actually connecting all of the pins in the implementation that we are testing. And also we could write a test bench for it. So I thought I also wrote some unit tests for it, because why not? So yeah, it's not very fun to read, but it is what it is. And we can test it like this. All right. So it will run all of the tests. Yeah, there we go. So if we print the wrapper object, we will get the address map, like so. So I thought, let's do some rewrite, make this simpler. So one limitation by having this read-write thing is that you cannot have one address that is both a read and write that returns different signals. And the reason why that matters is because sometimes you might want to be able to only show a part of a register. So here, for example, we are able to write the key in full, but we can only read the 3 least significant bits. And then, yeah, the reason is because, yeah, you don't want to show the full key, but still be able to leak a few bits, which, yeah, I don't know. Sometimes you want to do that. So let's add that feature. So instead of doing like this, we can remove the read and writable. So we only have read and write, and we can even yeah, let's just do like this. So we have 2 bits, and we will remove the read and writables, and yeah, let's rewrite this a little bit. So instead of having endpoints, we could have readable and writable dictionary instead. And then we can just add endpoints to the list in question. Maybe. Or maybe we should keep this API, because we can call this from the outside and we don't want to specify any self thingies. That doesn't make sense. I guess this is cleaner. Okay, so Yeah, let's this is not nice either, because we need to know which endpoints we are operating on. Yeah, and we can do this assert later on instead, so that we try to add it, and if we are overwriting something, we're just asserting then. Okay. Yeah, this still applies. So we're basically checking that all of the signals that we're adding are not wider than what we are supporting, because if it is, we're never gonna be able to set those bits. All right. So here we are iterating over the signals, and if it's an array, we are recursively adding each entry of the array into yeah, it's recursive basically. So you can even have arrays within arrays, and it will work, I think. Yep. Okay. So now we need to rewrite this a little bit, I think. We are operating on the endpoints, and we want to update it with, let's see here, did something with my audio. There we go. Okay. Yeah, so the key is the address, and the address is the start. Right, so now that I think about it, this is not good. We need to add the start address here as well. So I should probably add a unit test for this as well. Forgot about that. Anyway, so we're starting at start plus I. Yeah. And I guess here we can assert that start plus I not in endpoints. So basically checking that this key is not already present in endpoints. So I'm not super good at Python, so if we just do like so. Yep, there we go. No problem. So we can do that. Cool. So now we can remove that. And do we still need the flags? I don't think so. We can remove that. So we're only storing the actual signal in the endpoint array or dictionary. Okay, nice. And then here we right. I guess this needs to be rewritten a little bit so that we are actually yeah. So we need to print this twice, like once for the readables and once for the writables. I think that makes sense because, again, you can have different signals for the readables and different signals for the writable address. So let's do like this. Yeah. Yes, what we are doing here is that we're picking out, yeah, this doesn't apply anymore because we don't have a tuple anymore. So we, instead of S, yeah, we can do this instead. I usually use I for the index and V for a value. It's short. But still kind of makes sense. Okay, cool. What are we doing here? We are printing this. Should be fine. Yep. So you can do like this. So first we add the readables and then the writables. Cool. Then we join it. Should be fine. Now we need to rewrite this a little bit. So instead of filtering, we can simply do self.endpoints like this. This should work, but I think the unit test will not work because we are initializing the read and writables like so. So instead, all right, the addresses will not be. Yeah, right. So the way it worked before was that we got these addresses. So what we can do now is actually we can rewrite this into something that will still work. So I think actually if we do it like this, we'll get this one, R0, R1, and then right. This is also interesting. If we have addresses that are not writable, but we want to create a gap, we will probably need to add something in between, like this. But again, this only applies if we want to use this construction to create it. I mean, we can always call add endpoints from the outside. So this will probably work, but if v is none, continue. So this way we can have gaps in the no, this doesn't. No, this won't work. This gets a little bit ugly. If we want to sort of allocate null slots. Anyway, we can see if we can figure something out. So for now, we can just have placeholder signals like so. Yeah, let's do that instead. Okay, let's try out the unit test. Okay, it exploded. But at least we got some prints. We got 2 prints. Right. So we need to fix a few things. Here we have lines. All right. We should do like this first of all. Okay, I've messed up completely. A little bit curious why this happened. So I print it here, just double checking that. Yep, that seems correct. So we're printing it once. I'm getting this mess of an output for some reason. Oh, it's probably because of the names. So instead of calling it lines, all right, we should, let's just do like this instead. Yeah, no, what? All right. Okay, here we go. So now this makes more sense. So now we have readable address 0, 1, 2, 3, and then writable 0, 1, placeholder, and then 0, 1. So this should technically work, but it's not. Something, I made some typo somewhere. Right, so we don't need to do that. And instead of doing this, all right, we can simplify this so much. There we go. Right? Yeah. Okay. Almost there. Line 74. Right. All right. How do you enumerate a dict? Again, I'm not super good at Python. Let's do like this instead. Items. Right. And then we can do. Don't care about the. Actually, we do. Let's call it address and signal. This makes more sense. Should we call it value, perhaps? Signal is better. Lowercase. Yeah. So again, you get the index or the key. You get the key and value, and no, wait a minute. I think I'm not thinking straight. Right, we get an address in. yeah, let's call this endpoint instead. So this is like the endpoint address, the key. Or let's just do k and v, it'll be simpler. So yeah, so for the key for each address, so for example, let's say we get a 3, or it's actually right enabled. So let's say we get a 1, we want to apply this one. Then we get a 1 here, so we do m.case 1, and then we want to apply the right data to the value, so v. So for address 1, we're gonna change the RW1 signal. Nice. This makes sense. So let's just do same thing, but the readables. And again, we're taking the signal and outputting that onto the read data. Yeah. So let's try again. Oh, unit test pass. Nice. So now we kind of want to get rid of these. How do we do that? Yeah. So if we instead do like this, I guess one way we could do it is to actually have yeah, one way to do it is to just make it even simpler, and just have a key value with address and signal, because then you can have a sparse, or like, yeah, you can have gaps in the dictionary. So I mean, this is one way to do it. Yeah, I am not really sure. You can design this in, yeah, it's easy to over design, and I guess it's boring to watch. So maybe we should just leave it here and say it's good enough. Let's continue. So did I? Right, it will break if we have none, which makes sense. So I guess here, yeah, this is gonna be ugly. Let's just keep it this way, and we can continue. I'll fix that later. Yeah, let's see if I guess we need to adjust our crypto XOR example, because now we don't have a read and writable. We need to add this here and here. Let's see if it builds. Yep, it's built, no errors. So just gonna take the word for it. It looks good. We have a few loots, and the timing seems reasonable, slow, like 250 megahertz. Yeah, seems reasonable. And now I made a similar top module for the CXXR20, and this time we also need to move down the enable and counter, and then copy those two over here. This one takes quite, okay, broke. Why did it break? Bus wrapper, line 37. Okay, I'm gonna add some prints. So I guess the problem is that I'm adding an array here, right? Split into words. Yeah, this is splitting it up into a list. Just gonna disable this and just see if it builds. No, it doesn't build. Okay. What am I missing? So I'm essentially doing the same thing as here. Just have a little bit more endpoints. And start plus I, not in endpoints. Oh, it's starting over again. Ah, okay. I guess the problem is, yeah, okay. So we need to, oh, this gets ugly. So how do we want to solve this? We could do it like this, I guess. Yeah, that seems to work. And it looks like we get a decent address mapping as well. Now it's off by 1. Oh, we need this one as well. So for the data ready, I guess we need to add an placeholder. Yeah. And then for the key and nonce, in this case, I've just not exposed them in the readables, which is, I guess, fine. But yeah, now we can build it again. I'm gonna clean it up a little bit. Error. Okay. Okay, here we go. So for some reason, when you're building with nMigen and yosys and press Ctrl C, while yosys is running, it will not kill the process. Okay. Yeah, I guess this takes a while because of the logic is it's a little bit more complex. Okay, it's done. So this time we are using a lot more LUTs, and we end up with a fmax of 30 megahertz, which is reasonable and sort of what we are expecting. Because this particular implementation is, what's it called again? It's doing 8 rounds per iteration. This doesn't, that's not really true. Anyway, it is, this is the quarter round, and we are performing the quarter round 8 times per iteration. This is happening always. Yeah. So anyway, let's go back and finish up what we're doing. So what have we done today? We have improved the bus wrapper. It is now slightly simpler. This logic is very straightforward. We have chip select, we're checking for write enable or not, we're switching on the address, we're iterating over our writable items, and we're adding case statements that are updating each signal in that list with the write data. And then for the else, which is not write enable, we are switching on the address again. We're iterating over the readable items. We have a case for each address in those, the key being the address. And here we're using the comp statement because we don't need to clock out the data. We can just point to the signal that we're having. If I'm using sync here, it will be delayed with 1 clock cycle, and it will use up 32 more bits as sort of an output buffer, which might be what you want, maybe not. I'm not sure. So I can add it to do here, and just write maybe change to sync, and yeah, because sometimes maybe that is what you want. It depends. Yeah. So anyway, by having it this way, the latency is shorter as well. When we are reading data, it needs to be sync because we are taking bits from the outside world and we are sampling them and storing them somewhere. So it has to be sync. Okay. So that is the bus wrapper. I hope it's understandable. And again, maybe we should improve on this later on so that instead of taking an array, we take a dict where users already specify a sparse address and signal mapping. We can do that later, but not now, because it's gonna... Let's just continue. So now we have that. So let me commit that. All right. So I before doing that, I I imported the code for the Cha-Cha 20 from SecWorks, this one that I showed before. This is a nice core that is being used in both silicon and FPGAs, I think. Perhaps not. But anyway, it is proven to work. And we have some performance data on it, which is really nice. So what I did was to import that code, like so. I've just downloaded the Verilog files. And then I created a top module for it in nMigen. So this file here, it again uses the platform files that we have already written. So these sort of test files, test platforms. And then I'm picking those signals, and I'm adding these Verilog files using platform.addFile. So this is how you add existing Verilog, external Verilog code into your nMigen project. There are more ways to do it, but this is one way. Yeah, so here I'm adding all of those files. And here I just copied a little bit Verilog from the top module. And here I am creating an instance of the Cha-Cha module. So in this file, we have module Cha-Cha. So this name here, I'm instantiating that with these signals. So the way you do that in nMigen is that you write I underscore lowercase. This will connect a signal with the following name, CLK in this case, with a signal from the nMigen side. So in order to get the synchronous clock signal, the default clock in this case, you just type clock signal. And I got some problem with the reset signal, so I just used the const one. But yeah, I can fix that later. And I connect the CS and write enable, and these are again from the platform. So here I'm hooking up those signals to the Cha-Cha module. And then I do the same with output as well. And that's it. So this is sort of an nMigen adapter for the Verilog code. So by doing this, I'm now able to run this Python file here. Before I do that, I'm just going to clean up the build directory. When I run this now, nMigen will create project files, like build scripts, that are instantiating all of this and adds this top level generated Verilog file for hooking up the signals and synthesizing it. So it's this simple. So if you have some Verilog file and you just want to synthesize some test project, yeah, you can do that like this. Instead of having to open up whatever tools or writing some make files or whatever, you can just do this. It's really simple. This is gonna take a little while, but we can look at the timing report, I think. Yeah. So here we're using 4,500 LUT4s, which result in 3,500 slices. Right. So again, this is the output from NextPNR, and it's working on routing it. And here it's identified the critical path, and I think you should be able to see what it is. Yeah, exactly. Here you can see the path. So unsurprisingly, it will be the actual, let's see here. Yeah, the quarter round the actual bit twiddling. So in this case, we are at exactly this statement. So if you want to, you can follow this chain and see like exactly what is going on. But yeah, in our case, it's of course this code that is moving around the bits. That is the critical path. And then again, we get the timing report here, in this case 45 megahertz. And we have to remember now that this implementation is only doing 4 rounds per clock cycle. So it is not performing 2, or I mean 8 rounds. It's doing 4. Or to be correct, it's doing 4 quarter rounds. So 1 full round per iteration. And my implementation was doing 2 full rounds, or 8 quarter rounds. So anyway, that's it. That's it. We have our top module file. Looks like this. And we got our synthesized code. Perfect. We have our bit stream. So in order to sort of have something that I can test and compare with, I also changed the top module. Instead of using this one, the cha-cha.v, which again, if we look at it, it exposes these signals, and it does all of the address decoding and all of that. And instead of this, we are going to use bus wrapper. So here's the top module that is, again, including the core and quarter round. Those 2 files are the ones that are performing the actual work. And here I'm creating an nMigen. I'm hooking up that module with bus wrapper. So here are the intermediate signals. So the key and quarter round and the round numbers and counter and all of that stuff. And then I'm instantiating the cha-cha core using these signals. So at this point, we have our core and we have our signals. And now I create the bus wrapper where we are, again, creating or generating a top module or a memory-like module. And we're connecting the signals to the outer world. So these come from the platform. These are pins, actual pins on the FPGA. And here I'm adding some endpoints. And here I'm adding some more endpoints. So because we have rewritten the API a little bit, we need to do some changes. Yeah. So the read and writables need to be added twice. So actually, now that I think about it, no, it's gonna be messy. Keeping things simple is always a good idea. So instead of doing something smart, I'm just gonna do read and write for control. So the key thing here is that we have the same address, but that's fine because they're gonna end up in the 2 different slots. And for key length and rounds, we need to do this twice as well. Yep, now we have support for that. So instead of having these as read and writables, we can add it as read and writables. And instead of doing like this, we can do a slice like that. So let me explain what's happening here. So in the SecWorks code, they are exposing the key like this, the 3 least significant Oh, okay, wait a minute. What are they actually doing here? They're actually exposing the full key with 3 bits worth of address. Right, okay, now I get it. So, oh, okay, so again, I misinterpreted the code a little bit. So I implemented something that was not actually needed. So what they're doing here is that the address is, yeah, some address, but the 3 least significant bits are start from 0 and count up to 7, and there are 8 key registers, and here they're simply accessing the key registers based on the least significant bits of the address. So the way I read this code was basically something like this instead. So that, yeah, you're able to read out like the 3 least significant bits of the key, but that is not the case. So I was simply reading the code wrong, but that makes things simpler. Let's just do like this instead. Yep, there you go. And then we have to do the same thing over here. And there we go. So this is mapping up the signals with an address and some access, read and write. And then we print the address mapping and elaborate. So let's see how it works. Let's wrapper. Oh no. Okay. So it didn't build because I made some mistake. On line 46. So this should. Didn't I test this? Yes. This feels wrong. Something is probably wrong. Just a little bit curious what broke. So I'm actually gonna cancel that and try to figure out. So we end up here on 24. So it's when we add the read registers, and oh, is it? Okay, so if we don't have any signals. Oh, okay. So it's a special case when the arrays are empty. I guess I should handle that. I can just this feels a little bit like a hack. Actually, this is less of a hack. Yeah, that is less of a hack. Maybe it should be like No. Yeah, this would be more correct. Hmm. Actually, let's. I think this is actually not correct. Hmm. Oh well. Hmm. So what are we doing here? We are. Let's say we start at address 5. And let's say this is doing one recursion. Then this one will be 0. Yeah, this will not be right. I need to add a unit test for this. So okay, let's see if that makes any sense. Exactly. So now we get a bit of a problem. So we need to increase the start position with this. Yeah, now it makes sense. Then end is not really correct. So last I, yeah. This is crap. This is not going to work either. So if you have an array within an array, gonna be nasty. So if we have something like this instead, let's see here. Need to create that. Yeah. So now we have a deep array, an array within an array. This should end up at address 0x10, this one at 11, this one at 12. And I don't think that will happen. No. The reason for that is because I'm not thinking straight. So let's create something called offset instead. Well, yeah, I guess I should solve this in a different way. But for now, we can just do that works. That's the important thing. Okay, so getting back at what I actually wanted to do. What was that? Right. So we have this top module, and that seems to work. That's perfect. Yeah, that seems to still build. Yeah, no, this doesn't work anymore. Okay, maybe I should just solve this properly. Right. Okay, does this make sense then? So we increase the offset with the number of entries added. So in this case, it's recursive, and we get whatever we get. And in this case, we add actually 1, because we only add 1 signal in this case. Damn it. So what am I missing here? So, I mean, this looks pretty fine. No, it doesn't. It increases. Oh, okay. I get it. We can get rid of the I here instead. Yeah. And now this makes sense. Now we can add the assert again. So we have a start and we have an offset. We increase the offset in the simple case. We increase the offset with the return value of the recursive one. Yeah. And here we should have offset as well. Yes, now it should work. And then that means that we can skip I, which means that we can do signals.values. Oh. Right, just do like this. There we go. Now we have the assert. And it looks like it's working. So let's try the unit test again. And let's change the unit test a little bit so that we have the array within an array. Like so. Okay, now it breaks. Still don't really understand why this breaks. So I mean, we never get here. That's weird. Oh, right, because it's an array within an array. Oh. Okay. This is. This you can do like. No, but this is horrible. You know what? I'm just gonna skip this the nested case, and let's solve that later. We can do. Yeah, that works. That works. Okay, moving on. Time to do some more interesting test. It's 8:30. But yeah, I think it is time to do some C++. So I want to write a CXXRTL top level tester thingy that can, yeah, it doesn't have to do too much magic, but basically be able to test nMigen together with Verilog. So I'm just gonna, let's just do one more thing. Yeah, okay, that works. Perfect. I just want to double check that my code works. So now I think I'm gonna just make a checkpoint commit. And now we can start working on the CXXRTL. So first of all, what is CXXRTL? So it is a part of yosys. And I think, yeah, this is the, it's one huge C++ header file. It's actually not that huge, considering what it does. Okay, there are a bunch of extra files here. But it's quite cool. It converts, or it acts as a backend for yosys. So just like you can synthesize RTL, you can synthesize it for an ECP5, or you can synthesize it for whatever FPGA you want. But in this case, we are synthesizing it for C++. So instead of getting a bit stream or getting, what's it called again? Netlist for a specific FPGA, we get C++ instead. And the cool thing with that is that instead of simulating the code in Python, we are simulating it in C++, which means that we can use Clang to compile and optimize the code for us, which is really cool. So the performance here is actually significant. It's really, really good. This is sort of a leap of faith. Maybe it will work, maybe it won't. Let me just, I have a test where I'm using, what's it called again? I'm rendering a picture in real time using nMigen, and it does not build. Crap. Okay, almost there. So the question is, do we want to spend time trying to fix this or not? I don't know. I think it's probably too much work to do on stream. Anyway, we can still look at this code a little bit and get some inspiration for it. But essentially, what's happening is that maybe we can run the Blinky. Yeah, that we can do. Okay, it's compiling and running. Okay, much better. So the problem with the previous test is that it's doing some complex stuff with the black boxes and SDL, but this one is way more simple. So again, this is in my Pergola project, which is my other playground nMigen project. But here I have made a logic block, which I call Blinky. So this is taking an output and an input. It's creating a timer. And then in the elaborate function, we are performing the logic. We are counting our timer +1 for each clock cycle. And then if the button is pressed, the LED will always be on. Otherwise, it will show the most significant bit of the timer counter. So this is like the logic for Blinky. Then here is a normal nMigen test case where we use the simulator and we do this def process yield. We assert various properties, and you can get a VCD file, just like we did last time with the SHA implementation. And then there is also formal verification support. It allows you to apply formal methods to the logic and essentially prove that your logic is correct as long as your assertions are sane. But that's really cool. We can talk about that some other time. But that is really, really cool because it can find bugs instead of you defining what bugs to find. Like when you write a normal test case, normal unit test, you're saying, when I do this should happen. But with a formal verification, you can basically say, this situation cannot happen. And then it will crunch the numbers for you and eventually come out with a result telling you, oh, you're wrong. This can actually happen, and present a test case for you. So that's really cool. But we're not doing that today. Today, we are doing the CXXRTL. So again, what this does is it sets up a top module where we instantiate the Blinky, and then we are using the CXXRTL support in nMigen that generates a C++ file that we then add a main method to, where we perform the actual test case and print the output and so on. And then we compile it with the Clang And finally, we execute it, and we also get a VCD file. So that is actually what just happened here. I think, yes, exactly, because we ran this. So I should have this file here. So after running this, we got this file. And yeah, you can see it's a VCD file. So all of our logic is inside here. So that's really, really powerful. So my idea now is to set up a similar test case for the SecWorks Cha-Cha module. And then eventually we can switch out the implementation to ours. And that way we will be able to essentially test that our implementation matches this implementation, but with different properties, such as a different number of rounds being executed or different number of cycles per operation and so on. So again, yeah, we need to write some C++. So how do we do that? Yeah, I mean, I'm lazy, so I'm just gonna copy this. So yeah, we're gonna copy a lot. So let's call it like so. And then we can go back here and copy this. And then instead of doing this, which is building an actual synthesizable thing, we are gonna do something else. We're not using this. We are using I guess we can do it like this instead. Okay, so instead of doing this, where we are asking for pins from the outside world, we need to create them ourselves. So there we go. And instead of this, I guess we can just do like this instead. Just remove this completely. Remove that as well. The question is now, how do we add Verilog files to CXXRTL? I don't know. So this will be sort of exploratory. Hopefully we can figure it out. Yeah. Okay. Yeah, this still makes sense. Yeah. Clean it up a little bit. So let's have a look at the implementation here. How do I add Verilog file? I suppose it will be a black box. I'm not sure. So I cannot really do this. So let's think a little bit. First of all, let's expose the ports that we want, which in our case is basically this. There we go. And then let's see, takes black boxes. If that is a string, what does it do with that? It will do this, read ilang, and that will not work, I think, for Verilog files. So yeah, I guess we need to do something ourselves. So yeah, this will be interesting. I wonder if I can even access this from the outside. Let's try. Maybe we should try with something really simple first, and then do this. So let's do it like this. First we do it like that, and then we can just do something much simpler here instead. So yeah, let's we create a module, and then call this foo, and then we have a clock, reset, and let's call this just n1. Okay, so now we have this like so, and then we need to write some Verilog. I'm not very good at Verilog, so I'm just gonna copy some. So we need a module. Okay, cool. So okay, so now we have our module. Then we need to end it with nModule. Cool. And yeah, right, always at +h. I guess we can just write something like this. So essentially it will blink, and it will also care about the input. And we can skip the reset, just to keep things simple. Okay, this makes sense. So now we have some Verilog code. Now we want to add that to our project. So we need to replicate this. But we want to change these to basically include Verilog code. So yeah. So I guess I can just basically copy this. And we can put it here. This will not work, of course. We can do that. Okay, that's perfect. And we can do that as well. That's really good. Nice. So let's do like that. And yeah, this is nice, but let's not do that. Yeah, this makes sense. But instead of read ilang, we do that instead. And right, this is I don't know if you can do like this. Maybe. With some luck, this works. Let's try it. So again, we need to do this part, but up here. So let's see if we can do that. We want to expose foo and bar. Right. Okay. Who knows? Who knows what's gonna happen? Let's try it. Okay, it cannot import RTL IL. That is because that is. I should do like this. There we go. Okay, unknown cell example. That's interesting. So let's so here I'm. Oh right, I can probably not do this. Let's look at the black box example. That didn't work, but where is it? Didn't I have it here? Here we go. Right. Okay. All right. I forgot to instantiate it. I'm stupid. So instead of black boxes, we should do Verilog boxes and call it example. And let's call this variable with the code example v. Got an unexpected Verilog boxes. Yeah, that's of course correct, because we should use this one. Yeah. Don't think we are gonna need that one. Non-type. Okay. Oh, right. Okay, check it out. It actually built. So this is pretty cool. So I wonder if it actually worked. Do we have foo and bar? We do. I think. Huh. This is quite cool. So let's just make it a little bit more interesting. And how do you write this again? Like this, I think. Oh, not that one. Wire 32. Value 32. Nice. Line 56. Yeah, okay, so that's these ones. And then where is our black box then? Is it this one? Yeah, here it says Verilog. That's really cool. So if we make this a little bit more interesting, we do plus 42 instead. Yeah, there's our value. Really cool. So what have we done right now? We have, by just adding this tiny little snippet, added support for including Verilog black boxes in nMigen's CXXRTL. Yeah, cool. So let's try to build and try this out. To do that, we do this. Yeah, let's see if I can remember. Right. So there we go. Actually, I'm gonna copy all of it. It's still quite a lot of code just to do very simple test bench. But all of that will be improved in the near future. We want to do this now, so we can't wait. So anyway, let's do like that. What are we doing? We have our output source code. We have our root. Create the build directory. Top.cpp and elf. Writing to it. We're writing the output we just created, and then we're writing the test bench. So what do we do in the test bench? Yeah, we want to write a VCD file. And yeah, this doesn't really match what we're doing, but let's see here. Okay, so here I'm just setting some value. We could do stuff like setting foo. Yeah, let's set foo to 100 after 8 cycles. And we step the clock. Yeah. And instead of printing the timer, we are printing foo and bar. Perfect. There we go. And we are writing the buffer. Perfect. We need a subprocess. Okay. What are we more doing? We are writing. So now we have written the C++ file. Then we're running Clang. We're including yosys so that we get the header file for CXXRTL. And then we are executing the elf and we are exporting a VCD file. So let's try it. Let's see what happens. Okay, it seems to it actually runs on the first try. That's scary. So, doesn't seem to actually work. Am I using different names? CLK, phone bar. Okay, right. I should do. We can do it like this. Perfect. It will be a little bit more interesting. And as you can see, yep, it increases. Perfect. And where is the header? And just to show you, yep, here we have everything. It's gonna be hard for you to read, but yep, the value increases, and we have all the data here. Perfect. So this is really cool. Now we have CXXRTL. We can include Verilog files. So what are we gonna do now? Now we are gonna take this code and move it down here, basically. So we need to add these files. And in order to do that, we're gonna take the, let's see here. Yeah, we're gonna have to do this and do that down here. Right, so that is fine. But now we also need Verilog boxes. And yeah, this is gonna be a little bit ugly, but let's do that. So what are we doing here? We create a dict with the key value. All right, it needs to be a column, right? And there we go. So here we are generating the C++, which will include the Verilog files. And yeah, now I can copy this code, which we just wrote, and put it here. And then we need to change a few things. So first of all, we need to add our let's see here. Actually, we don't need to do anything. We can just ignore this ignore this and just step. I mean, we can print a few things just because why not? All right, we need to actually induce some values. So, right, we need to set chip select to 1. Chip select needs to be 1. And then we can say, for example, write enable should also be 1, and address should be, for example, the what should we take? Some status register, for example. Init, right? How do you set that? You set the control status register. What is control? That is 8. Okay, so we set the, let's see here. Address is 8, write enable, and then we need to set the data right, and the value should be 1, I think. Yeah, init. Yep, and then we stop. So we can actually move this here, and just for the sake of just to see what's going on, we're gonna step the clock before and after, and we can go for 64 times. And we also need to call it. So let's call this okay. Let's see what happens. Okay, it broke. Line. Okay, can remove these. Right, I'm using the wrong. This one. I should use this one because this is our implementation. Okay, it's doing stuff. Something is not good. Now I'm not really sure what's wrong. Maybe there is too much code. I don't know. We can actually, no. I'm just thinking like it should be enough that I add this instance. But let's just start simple. No Verilog boxes. Unknown cell cha-cha. Okay. Because I am probably... All right, it's this one that fails. So if we add that one, it will complain. Cha-cha core. Yeah, that's this one. Okay, it has unknown cell cha-cha QR. Okay. So I don't know why it complains. Like I don't really see what the error is. It is definitely doing something. Maybe it doesn't like that it reports warnings. No, it's actually a yosys error here. Replacing. Okay, but that's only warnings. That should be fine. So I guess my problem is that I should look at this code perhaps and just see why. Okay, so the return code is non-zero. I'm gonna do something really ugly here and just say return code is 0. And just see what happens. So now it builds, but okay, maybe yosys doesn't return anything. Yeah, you see there's just white space here. So for some reason that I am not sure about, we are unable to synthesize the C++. And I honestly don't really understand this error message. Oh, I'm gonna do something so that I know which file is wrong. So I'm gonna add file name to this. Box name. This might or might not work. Okay, now at least we know which file is wrong. So in the Cha-Cha core, we get these warnings. Replacing memory with... Okay, but I mean, this is not really an error. It's just a warning. I honestly don't understand why yosys is not succeeding here. It's really strange. I mean, this is nothing strange, really. Oh, I have zero knowledge about FPGA programming. Can you please teach the basics or give some reference? Sure. Where should I start? First of all, I'm not an expert. I'm just learning. I'm using something called nMigen, which is what you're seeing here. It's written in Python. Yes, the simplest thing we can do is to look at Blinky, where we are basically blinking an LED. So, yeah. The structure of the program is that you create these elaboratable classes where you are... these are like pieces of logic that can affect the system in some way. You have synchronous and combinatoric logic. Synchronous logic is applied for each clock cycle. So when the clock ticks, this statement is executed, basically. And in this case, we are taking the timer, which is a register, a signal of timer with bits. So it's a 24-bit signal, and we are increasing it, and we're applying it to the same signal. So every clock cycle, this will be updated. And this will happen. It's not like C programming or imperative code. It will just happen all the time. Then here we have some combinatoric logic, which is different from the synchronous logic. This one will always happen. It's not connected to a clock. It's just always connected. So in this case, it is an if statement where we check if the button is pressed, then the LED should always be on. And if the button is not pressed, in the else statement, we will set the LED to be the most significant bit of the timer. So yeah, this is a blinky that will turn on the LED forever if you press it. Like while you're holding down the button, the LED will light up. Otherwise, it will blink. So yeah, that is like the most basic program you can do in nMigen. So I've chosen to write my code in nMigen because I like it. It's Python, it's scriptable, it's extendable, and so on. And also it's open source and it synthesizes to, or it hooks in together with the open source toolchains very well. So it's really nice to use. Yeah. So anyway, what we were doing here is looking at a CXXR20 crypto algorithm implementation that we want to test using something called CXXRTL, which is a way to convert yosys internal representation and Verilog and other types of HDL source into C++, similar to Icarus, Verilog, or Verilator. The difference is that this hooks in very neatly together with the open source tools, yosys, which is a program that, yeah, I'm probably gonna get the terminology wrong here, but it does the first stages of converting your HDL to something that is understandable by your place and route tool. So, and in this case, we don't really care about an actual FPGA. We want it to run on C++. So anyway, what I have been doing here is to create a I've extended the implementation in nMigen that generates yosys scripts that create a C++ project. So I've made some slight changes to that so that we can extend the project with the Verilog code. So here I want to use this already implemented CXXR core in Verilog, and I want to mix that code with nMigen code. And to do that, yeah, I had to do some changes. And right now, just a few moments ago, we were able to build Blinky together with oops. So here I'm synthesizing a project using Verilog mixed with nMigen. And it's a very simple project that only counts a little bit, but it works. Now I wanted to try to do the same thing with the CXXR core in Verilog. But for some reason, I get a few warnings from yosys, and for some reason that halts the build process. nMigen can't simulate Verilog directly, right? That's correct. Right now, at the moment of speaking, it cannot do that. But in the future, CXXSim will be able to do that. So I haven't really, I don't really know that much about it, but I think there seems to be plans around that, so that you should basically be able to write, let's see here, this style of test bench, this style of a test bench, where you use Python to drive your workflow. And instead of saying sim.run, you do cxxsim.run, something like that. And what I'm doing, and that doesn't exist right now. But because that doesn't exist, I still want to do that. I did this quick hack. So in short, I just done this little change where we were able to add Verilog code into the project. And as I explained just a few seconds ago, I'm not able to synthesize it because I have warnings. So these warnings should be fine. They shouldn't really lead to any problems. But it seems that inside of nMigen, it's very aggressive in catching those return codes. All right. We have this thing called ignore warnings. Maybe I should read the code. So yeah, let's do that. But here it says actually ignore warnings equals true. Okay. I should just do that. Okay, that didn't work. Maybe this was the wrong line. No? Okay, let's see here. It would seem that this doesn't really have any effect. Yeah, it's there. So line 108. Okay, so actually, so yosys is not just casting an error, it's actually returning an error code. But let's just not care about that. Let's see if it continues. Okay, so this time we got a little bit further, but I'm not sure if this is correct either. So let's have a look at the top.cpp. Okay, so again, we just get a few white spaces here in the beginning. This means that yosys output, yeah, it's nothing. Just double checking here. Yeah, so yosys is not able to output anything. So I don't know, maybe I just found a bug in yosys, or something is wrong with the code. But again, I'm able to use the same source code. Let's see here. So I'm using these Verilog files, and here I have a top module written in nMigen that use the same source code, and I connect it to the outside world with these platform thingies, and just to prove that it works, I can run this, and again, I get the same warnings that I did up here. These. But it works. So yeah, who knows? So anyway, yeah, I know that works. But this doesn't. So the question is now, can we improve verboseness inside of yosys? Most likely. I just haven't worked that much with the yosys. I usually just use it, and I'm happy when it works. Can we do? Wow, that was a lot. I didn't know that you could have this many options to read Verilog. Maybe we should add this debug. Let's do that. Maybe we can get closer to understanding to why it doesn't work. Actually, let's do this in steps. So, okay, now we got some more stuff. Oh wow, this time we definitely got code. 3,000 lines of C++. That's cool. So the difference was that I commented out this delete Verilog initial trigger. I have no idea what that does really. Okay, wait a minute. So this one contains the RTL IL from the nMigen code. So I'm just going to print that. So this is our top module. This is the top module from our nMigen code. What do we actually do here? And does this seem to be correct? We have the cha-cha top, which is of the cha-cha cell type. And we simply connect all the things together. These seem to be correct. 32 bits, 8 bits, yeah. Very simple, very clean. This is actually surprisingly easy to read. I haven't actually had a look at nMigen, or I mean yosys IL at all. But anyway, so now we know that the code looks decent. If we skip adding the Verilog boxes, what happens? Yeah, yosys will complain because it cannot find the cha-cha implementation. So all of that makes sense. What is this Verilog initial trigger? I don't know. It doesn't seem to do any. Doesn't seem to have any big implication. So let's remove this again, just for the sake of testing. No, it doesn't work. Okay. I was a little bit worried that having a dot, a period in the name would be a problem. All right, let's do like that. Okay, so how do we continue? It's really frustrating because we are so close. Because we have the blinky working and this one not working. I guess we can. No, I mean adding. Maybe we can add some arguments to this one. Set the debug level, debug information. Yeah. Oh wow. Oh, here's a lot of information. Yeah, let's just add some debug information. Okay, I got nothing. I'm just fumbling around now. The annoying thing is that I don't really know why yosys is bailing out. Um, like it would be nice if it could print like internal debug information. Yeah, maybe this one. So instead of Q, let's have V. Mm, okay, slightly more information. Maybe. Okay. So I don't know. It's strange because if I comment out this one, yeah, it definitely builds more stuff. Oh god, it's so much. Um, yeah, let's see if I can remove the output print. Hmm. Okay, now I don't get any output. That's also weird. So this is how it may look when it sort of works. Yeah. And so it's spitting out 4 to 10, 5. Why is there? All right, because it's the 5th step. Okay. Proc clean pass. So it seems that we are getting as far as we do when it works, but then it just bails out without any information. I don't know. Okay, I guess we want to get more logs than this then. Yeah, it's a shame, really. Would have been fun. Yeah, this is for the actual code. So if I increase this, it will generate different, like more debug information in the code. But I want more information in the process. I am not sure. Okay. Well, I think maybe it's time to wrap up. I don't know. It feels like I'm not really getting anywhere. And this, yeah, I should probably post in the IRC and see if we can get some help. It feels like the issue is somewhere inside of yosys, or I'm probably holding it wrong, but I don't know why. There's probably some information that I just don't see. So I guess, yeah, it's a little bit sad to end here, because we haven't really managed to do what we wanted to. But it's been an interesting journey anyway. So until next time, thanks for joining.